Okay, today we're going to talk about how atoms combine. So there's your heading for today, how atoms combine. Now, if we just look at some things, you don't need to write anything here, okay, but just look at some common examples of atoms combining. Two hydrogen atoms combine with one oxygen atom to form water. And water's chemical code is H2O. Oops. So two hydrogen atoms with one oxygen. You see H2 means there's two hydrogens. And then O, if there's nothing after the O, that means that it's just one. So if there were two oxygens, it'd be H2O2 or H2O3 if there were three. But since there's nothing behind the O, it just means that there's one. Another example, one carbon atom and two oxygen atoms combine to form carbon dioxide, CO2. So one carbon, so that'd be C. If there's nothing after it, that means that's just one. Two oxygen atoms combine, so that'd be O2. So CO2, one carbon, two oxygens. Does that make sense? All right. So if we did this next one, 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms combine to form sugar. So take a minute, what do you think? How would you do this? All right, 6 carbon atoms, so it'd be C6, 12 hydrogens, so H is hydrogen, H12, and then 6 oxygens, so O6. So C6, H12, O6, that is sugar. That's the chemical code for sugar. Hopefully that makes sense. How about this one? One sodium atom and one chlorine atom combine to form salt. Sodium is Na. Chlorine is Cl. So NaCl would be table salt. There's only one sodium, so there's no letters behind it. There's only one chlorine, so there's no letters behind it. So NaCl. Go ahead and write this down. Elements chemically combine to form compounds. Elements chemically combine to form compounds. So with water, that hydrogen and that oxygen chemically combine to form water. Compounds cannot be broken down into individual elements easily. Go ahead and write this. Compounds cannot be broken down into individual elements easily. If I'm going too fast, you can always just pause it. Compounds cannot be broken down into individual elements easily. So I can't take water and I can't say, oh, I need some hydrogen, and pop the hydrogen off the oxygen and oh, now I'm good. If you think about, let's say you're in the water and you're drowning, okay? If we could break up H2O easily, then we breathe oxygen, so it would be, oh, we're in water, I'll just pop off the oxygen and oh, I'm good. It doesn't work that way because it needs a chemical reaction to come together or break apart. So I can't break apart compounds easily. Go ahead and write this also. Compounds have different properties than the elements making up that compound. Compounds have different properties than the elements making up that compound. I'll give you a couple examples here in a moment. Okay, so let's use water as an example. H2O, that's a nice easy one. Hydrogen is a gas. And from class the other day, we said hydrogen is super flammable, crazy flammable. So we have hydrogen, which is a flammable gas. We have oxygen, which is a gas that fire needs to burn. And when those chemically combined, we get water, which puts out fire. So we take two gases and we get a liquid. We take two things that fire like and we get something that fire does not like. So the properties are different. I kind of think of it as a team. If I have a volleyball team, maybe I don't have any star players, but I have 6 people that really work together well and they play well as a team. And they're a better team than maybe they should be because they play together as a team. Even though they're players, they don't have any star players. So on the other hand, maybe you play someone who has a bunch of great players, but their team isn't very good. So that's kind of how I think of it when I think of elements coming into compounds. Another example is sodium chloride, NaCl. Okay, sodium is, I believe, a poisonous gas, and chlorine is a poisonous gas. And when they combine, we get a solid that we sprinkle on our food to make it taste better. So sometimes the elements that make up the compounds are completely different than the compounds themselves. Looking at the periodic table from your little research, one of the things that you guys looked up is that groups go across the top here. So this would be group 1, 2, 3, 4, all the way to 18. Periods are down the side here. So period 1, 2, 3, 4 there. So if I asked you, for example, let's say I use nitrogen here, 7. Okay, so if I said what group and period is nitrogen, you would say group 15, period 2. Okay, or I could say I could ask you what element is period 3, group 17, and you'd go 1, 2, 3, 17, chlorine. Okay. So there was a couple questions about that on your little project thing. So hopefully that makes sense. Go ahead and write this down. Elements and compounds can be put together to form mixtures. Elements and compounds can be put together to form mixtures. A mixture is a physically put together group of things. Go ahead and write this. The components of mixtures can be separated back into their original form. A mixture can easily be separated. If you had Lucky Charms for breakfast this morning, that is a mixture. It is a mixture of milk and cereal. It's like the grain cereal and then the marshmallows. You could easily separate that out. You could drain off the milk, or you could, as a kid, I would always eat the regular cereal first, and then I'd be left with just a bowl of marshmallows, and then I'd eat those all at once. So you can easily separate those. Or I like Gardettos. I like those little chip Gardettos. Okay, there's pretzels in there. There's the little breading thing. There's a bunch of different things in there. It's a mixture. You could easily separate those. So a mixture is something physically put together that can easily be separated. Some common mixtures around us. You don't need to write this, but the air in this room there is oxygen, there's carbon dioxide, there's nitrogen, there's dust particles, there's a bunch of things floating around this room. It's a mixture. Tea and sugar or coffee and sugar could be a mixture. Ocean water could be a mixture. Okay? It's salt and water. I could evaporate the water off and I'd be left with the salt. Everyone's favorite Kool-Aid is a mixture. It's sugar and water. I could evaporate the water off and I'd be left with the sugar. I want you to write down homogeneous mixture in the first bullet. We're close to being done. Homogeneous mixture. Individual components mix completely and are not visible. The prefix homo means the same, which means everything mixes together evenly. If I go get a Mountain Dew from the teacher's lounge, okay, the Mountain Dew, the first sip and the last sip are exactly the same. Everything, all the sugar, all the ingredients are evenly mixed. Okay, it's not like the good stuff floats to the top or sinks to the bottom. It is all the same. It is a homogeneous mixture. It is evenly mixed. When you buy chocolate milk from the store, it's homogeneous mixture. It's evenly mixed. There's not chunks of chocolate at the bottom. On the other hand, the opposite is heterogeneous mixtures. The prefix hetero means different. So individual components don't completely mix. If you've ever made your own chocolate milk, a lot of times that doesn't completely mix. I'd probably call that a heterogeneous mixture. There's some chocolate that sunk to the bottom. Oil and water, heterogeneous mixture, doesn't mix. Even if I shake it up, it might appear at first that it's mixed, but if you give it a few minutes, it'll separate. That'll be a heterogeneous mixture. Growing up, we had grapevines, and my mom would make grape juice, and we'd put them down in the cellar. She'd can it and put it down in the cellar, and then we'd go drink it whenever. And the jars, before you open them up, you needed to shake them because the top half of the jar was almost clear. It almost looked like water. And the bottom half was bright purple because it was a heterogeneous mixture. It did not mix evenly. So homogeneous mixes perfectly together. Heterogeneous does not. Hopefully all that makes sense.